Okay, here we are, the last section of Chapter 1. 1-5, Day 2. The first thing we're going to do today is just kind of go through that whole process that we did yesterday, given that C and finding L and finding delta and epsilon. I just want to jump right into an example and take you through that process again, make you feel a little more comfortable with it. So if I have the function given by the quantity 2x squared minus 5x minus 3, it's a minus, all divided by x minus 3. Okay, first thing I want you to be able to do is sketch the graph and know if there's any discontinuities. Automatically you should know, oh, I can't divide by 0, so that I know there's a discontinuity at positive 3. So if we type it in, we should be able to see whether it's a whole or an asymptote. So if I go to the y equals 2x squared minus 5x minus 3. Oops, I forgot my parentheses. Yet the numerator has to be in a set of parentheses, and so does the denominator. X minus 3. I'm going to bring it back to a zoom 6. So I can see it's a linear function, but I know there is going to be a whole at 3. So put that over a little bit. Okay. All right. First thing I want to find after that is find the limit as x approaches 3 of my function. Okay, I'm going to ask you to do this algebraically on the test, but you can always use the calculator as a check. You can look at the table, or you can trace close to 3. If you try to trace right to 3, you're going to get that error because that's where the hole is at. If I go trace 3, enter, I don't get anything here because there's a hole in the graph. But if I just use my arrows left and right, at 2.7, I'm at about 6.5. At 2.9, I'm at 6.9. So I'm getting close to 3 here. Now I jumped over the 3, I'm at 7.3. So I've got 7.3 when I go back, I'm at 6.9. I wonder what y value I'm jumping over here. I'll bet it's 7. So we should be able to come up with 7. Or you can look at the table too. Table set, you can have it start at 3 and go 0.1 away and then look at the table values. Again, there's going to be an error there at 3 because of the hole, but I can see right after the 3 it's at 7.2. If I go up at 2.9, I'm at 6.8. You can see it's just jumping over a 7 here if you look at the average. But can you get that algebraically? Algebraically just means do the factoring and canceling. So you have to know, or have to remember, how to factor a quadratic. Well, we already know, you know what factors into the two binomials. You already know that x minus 3 is one of the factors. That's what's giving us the hole in the graph. That's a removable discontinuity. Now we just got to figure out the other one. Well, I know when I multiply the first times the first, I've got to get 2x squared. And when I multiply the last by the last, I've got to get negative 3. Not 2x squared, 2x. 2x times x gives me the 2x squared. Back to this. The last times the last has to give me a negative 3. If that's negative 3, this has to be a positive 1. And to get the negative 5x in the middle, that's your 1 times x is a positive 1x. 2x times the negative 3 is a negative 6x. When you add, you're going to get the negative 5x. So algebraically, I would show the factoring like I did up there. 2x plus 1 over x, times x minus 3 over x minus 3. Cancel. Now I can substitute 3 in for the x to see what the y value is going to be. So now I just show 2 times 3 plus 1. 7 is my limit. So now I know that this whole is right at 7. So my C value is 3, my L value is 7. Okay. Next question about this. How close to 3 must x be kept in order f of x to be within 0.02 units of the limit? Show this on your graph and then do the algebra. And then find algebraically. Okay, so what it's saying is I want to be within 0.02 of the limit. My limit, remember limits are y values, was 7. I want to go 0.02 away. Again, exaggerating. So this will be maxed out at 7.02. This will be 6.98. And then that's going to give me a window around the 3. And my goal is to find out how far away from 3 I can be. So we're going to set up that triple inequality where I use the 6.98 is less than or equal to my function. And my function, I want the, after I factored it out, is the 2x plus 1 less than or equal to 7.01. And now it's just solving for x in the middle. So the first thing I'm going to do is subtract 1. 5.98 less than or equal to 2x less than or equal to 6.01. Divide everything by 2. And I get 2.995 less than or equal to x less than or equal to 3.005. You will know if you did this right if these two numbers are around, right around the x number. One's smaller, one's bigger. If you don't get the number you are approaching in this window, you did something wrong, either on the setup or on your algebra. But because both of these are close to my x number, I'm pretty confident I did this correct. So my lower boundary here is 2.995 and 3.005. So if I pick any x number in between here, I'm guaranteed to have a y value that's within 0.02 of 7. Again, you're probably thinking, why is this all important? You're going to see in Chapter 2 where the whole foundation of calculus is based off of limits. So anyway, I still haven't answered my question. How close to 3? How far away is this from 3 distance-wise? 3 minus this is 0.005 away. This minus 3 is 0.005 away. So my distance away is 0.005, and that is my delta. The epsilon was right here. The epsilon was the 0.02. Okay. I think the graph helps a lot. Even if you label here, this is going to be my epsilon, this is going to be my delta. If you keep doing it, it's going to reinforce what we're doing here. Okay, I'll go next one. Oh, I didn't label that. We could call that example 1 before we move on to example 2. This is number 14 from your book, not that you need the book. We've got a function given as x minus the quantity x minus 2 divided by the absolute value of x minus 2. The question says, plot the graph, sketch the result, show the discontinuity at 2. All right. So let's just type it in your grapher. X minus quantity x minus 2 divided by, if you remember, your absolute values are found under, I believe it's math, over to num. ABS stands for absolute value. Absolute value of x minus 2. Okay, it doesn't make the big absolute value bars. It's got the letters to represent the absolute value bars. And now we'll graph. Okay, your calculator, if you have a newer operating system, won't be making this connection here. Mine connects. Technically, these are not connected. We knew there was going to be something goofy happening at 2 because this makes a 0 here and divide by 0, we got a problem. So the graph basically has 2 branches to it. It's doing this, and then it's doing this. And this jump is happening at 2. And I know that I don't have a 2 value, so I know I've got open circles at both of these endpoints because I can't have a value equal to 2 because that would make it divide by 0. Okay, so there's the sketch. It says find f of 1.99. That's really close to 2 coming from the left. And then find f of 2.01. That's coming close to 2, but from the larger side. So if I use our table, have it start at 1.99, go by 0.01. So at 1.99, I'm at 2.99. I'm almost up to 3. So on this branch is ending really close to 3. At 2.01, I'm at 1.01. So this branch is ending down really close to 1. All right, next question. Says, based on these 2 numbers, explain why there is no limit as x approaches 2. So why is there no limit as x approaches 2 of f of x? The reason there is no limit is because, remember, when your 2 fingers come together approaching x, they have to approach the same y value. These 2 branches are approaching 2 different y values, so no limit when that happens. So y is because you approach 2 different y values. As you approach x equals 2. I should use the word 2 here. Okay. The other thing I want to talk about, the other day when we did the trapezoid rule, the shortcut, the 1/2 y1 plus all the middle y's plus half the last y, there's actually a program for that. And I want to show you that. Oh, and I forgot to grab a calculator, so hold on while I run back and find one. Oh, whoops. Holding. Right back. Okay, found one. And I'm going to show you how to transfer these onto your calculators in class. But I just want to show you how the program works. Okay, the program is TrapRule. It says this program approximates the area under a curve from A to B using n trapezoids. So, I'm going to go back to that worksheet we had. Just to show you how it works. Remember the elevator one, the 1-4? We're going to find, using the program, distance traveled from, what would you do, 0 to 8 here. So this is back a couple days. We're going to type in our equation, which is right down here. So you don't have to do this, just watch, and so you know how the program works when you get it tomorrow. X cubed minus 21 x squared plus 100x plus 110. So it says enter the equation. I did. I hit enter. Left boundary. What's the, like we were going from 0 to 8, the left boundary obviously is the smaller value. So my left bound is 0. My right bound is 8. And how many trapezoids do you want to do? Well, we'll usually grab the program when we do a bunch of trapezoids. But if I wanted to check my work, let's see, how many trapezoids do we do here? 4. 4 trapezoids. This will sketch the graph, fix the window up, draw in the 4 trapezoids, and gave me the area of 1472, just like that. And then the author is just giving himself credit. Done. So I'm going to show you how to transfer programs. I'm going to give this program to someone in Rapid River. I'll give that to someone, and then I will show you guys in class, along with Gladstone people, how to transfer from calculator to calculator so you have that to use. Okay, so it's just another way you can check your work with it, and then there'll be some problems where it says use your grapher to do like 100 trapezoids. And you see this thing can do it in about 5 seconds. Okay, the last thing I want to show you is another way to do derivative or rate of change. And we've done the 2-point table and the 3-point table for that. So the last thing, we're going to write this one down, is last way to do derivative. So derivative. And this is probably the worst way, and you would only do this if you don't have an equation. You only have a sketch of the graph. So derivative without equation only a graph. We're going to use the slope of the tangent line that we draw in. And I know none of this makes sense until we actually do it. But just remember slope as being rise over run. Rise is your change in y values. Run is your change in x values. And that's what we were doing when we were doing our 3-point table. We'd subtract the y values, put that on top, subtract the x's, put it on the bottom, and divide. It is slope that we were doing. We just had the actual points. Well, if you don't have an equation, you don't have points. So I just want to go back to the same graph again. And if I asked you to estimate the derivative or rate of change at, let's go 1 minute. What you're going to do is go to the 1 minute. I guess you can just watch this at this point. And you want to draw a tangent line. Now a tangent line just skims the graph at that 1 point. It doesn't cross through. That's not a tangent line. Tangent line just skims it. A lot of people have problems with this. So what I'm going to suggest is that you take a point right before the 1, make another dot, take a point right after the 1, but really close to it, make another dot. Now you can kind of see those 3 are in a line, and you have to use a straight edge on these because we're going to be counting slope. You want the line to just skim the graph, not cut through the graph. This is not a tangent line. This is an intersecting line. Intersects it. We want to be tangent. We want to just hit that 1 point in the middle. And the other 2 points just kind of give me a guide how to hold my ruler. Now, is everybody going to do this perfectly? No. Okay. Once you draw your line, you want the slope of that particular line. And you've got 2 things you can do. You can just, I like to just count if possible. Like I'm going to take this point here, and I'm going to take another nice intersection right here. Find some nice intersections where you can just count along the graph. Okay, my rise, remember these were going by 25. My rise is 25, 50, 75, 100, 125. My rise was 125. And my run is, I'm counting by ones, 1, 2. So the derivative, or her rate of change at 1 minute, is going to be 62.5. And I would be dividing miles per minute by minute. We've done that before. It's miles per minute squared. Oh, we actually did it over here. Oh, I could have done this one at 5. Well, that's the one I should have done, and we could have compared. And because it's positive, I know that it's going up. So, draw your tangent line as best you can. I can help you with that. This tends to bother some people because they're not sure how to make that tangent line. But that's about it. So, that ends the chapter. Your assignment is going to be 1, 5 right here. 1, 5, day 2, page 28, 2 through 10 even, 12 parts A through G, 15. Then we're going to go back to page 23, so you can practice using that program. 9C and 10C. This is going to be using your program, the TRAP program that you have. And then 15, I actually think it goes on to page 24, is going to let you practice that slope and counting slope to get derivative. Okay, that ends the chapter.